Okay, so these chapters we simply just move the static problem to the kinematic problems. Okay, so this is a transition because after we finish the kinematic problem, and then final is dynamic problems. Okay, so usually for these chapters, one purpose, very important, which would like to provide a mathematical descriptions of the flow field. So our key point is, what is the flow field? Usually we use the velocity. We use the flow velocity to describe the flow motions. Okay, so the first is what is the flow velocities. And the second is the flow conditions. So I just, for example, I show in here the steady flow, uniform flow, laminar flow, turbulent flow, inviscid flow. So in our class, I will provide the certain definitions for the flow conditions shown here. Okay, and then the three important lines. First is string line, path line, and track line. Okay, the line just describe the flow motion conditions, but the different line have the different ideas. And because this topic we always focus on the kinematic problems, so three parameters shown here is the motion, velocity, and accelerations. Okay, so here is learning outcomes. So today I will just focus on this topic, and the next Monday I will we will have the quiz and just focus on these portions. Okay, so very simple. Just define the string lines, track line, and the path lines, and we have the two approach to describe the motion of the fluid flow. Okay, and then following chapters we have some properties introductions, but we will focus on accelerations. And the two equations, first is Euler's equations, second is Bernoulli equations. After we learned what is the Bernoulli or Euler equations, and then we can apply to the velocity measurement problems. And before that, always we assume the flow is linear flow. Okay, but the chapter 8, 4.8 starts from the chapter 4.8. We move to the rotational flow. We not always assume the flow is linear flow, so we will move to the rotation flows. Okay, so we need to go quickly. Okay, so the certain definitions for the three lines. The string lines, okay, there are some words, sentence, provide the definition, but I think after you read the sentence, but you still didn't understand what it means. Okay, so, but the key equation showing here is, if the string lines, that means the velocity factor is always tangent to the string lines. Okay, so, but the key equation here, for the string line, the spatial gradient is always equal to velocity gradient. The meanings, physical meanings showing here, what is the spatial gradient? Like the slope. Okay, the y changes divided the x spatial changes is equal to the velocity along y directions and the velocity along x directions. So that's what I say, the spatial gradient is equal to velocity gradient. And then in hydrology problem, usually we use the U and V and W as the different components of the velocity factors. This is for the x components. and this is for the y, and this is for the z components. So they are the velocity, but for different components. Okay, and x, y, z. And so based on this equation, if you rewrite the dx, dy, and u dv, u divided v is still correct. Okay, so any spatial gradient is always equal to the velocity gradient. It's a very important ideas for the straight lines. Okay, so the straight line and the path line. The path line is easy to understand. This is the point. You pick up one particle point, and this is the location for the T1, and this is the location for the T2, and this is the location for the T3. This is the fluid particles. So you fix one particle, but you track the particle at the different time point. And you have a 3 point, and you connect the line. This line is the path line. So the path line is fixed the one particle point, and you track the particle point at a different time point. Okay, but the straight line, what is a straight line? The straight line, this is you fix one point. You fix one point, maybe in here, but this is just the starting point, or you can call it is the reference point, and then there are many particles, okay, and this is the particle point at the time T1 time point, and all of the 4 particles has passed through the reference point, and in that time point, this is the straight line. And if right now this is our reference point, and this is the particle point for the T2 time point, and all of the particle point also pass through the reference point. And in that time, you connect all the particle point, and this is the straight line. Okay, so very difficult to understand, but the only one you need to keep in mind is the straight line. For the straight line, the spatial gradient is equal to velocity gradient, only for the straight line. Okay, so this is the figures. For example, you can take a look. This is a 2 time point. This is a time less than t0. This is a time larger than t0. And then we have different straight line directions. Okay, so for the path line, as I mentioned before, path line is you fix one point, and then you track the point at a different time point. So this is for this is the path line, because this is the t is equal to t0. After the t larger than t0, the straight line along these directions. So the particle change the directions at when the time larger than t0. So the path line is you check the one particle, but at a different time point. But the straight line, this is a straight line, okay? And you see the straight line, the line is different compared to the path line, because in that time point, previous particle also change the locations. But the path line, you just check the particle at a different time point. And here, at this time point, this is the previous locations. But at this time point, the previous location also change the locations at this time point. So the straight line is like these directions. Okay, so this is similar to if you do some smokings, and you can see the smoking cloud just move on the airs. So at this time point, the smoking cloud may be like this, but 10 minutes later, the smoking cloud will change a lot. Okay, so this is like but all of the smoking cloud pass through the initial point here. Okay, so maybe a little bit confusing, but you just keep in mind one definition is string line. This is very important. The spatial gradient is always equal to velocity gradient. It's especially for the string lines. Okay, so in that case, the flow we will call that is unsteady flow, because the particle motion and the physical properties will change with the time. As you see, the string line changes if the time point differs. So in that way, we call that is the unsteady flow. So what is the steady flow? Like here, the formula showing here. If the physical property is the flow velocity, the flow velocity didn't change with the time. That means that differential is equal to 0. So that we can say the flow is steady flow. So if unsteady, that means change with the time. Any physical property of the fluid change with the time, and we say that is unsteady flow. Okay, so the steady, unsteady is related to the time. Okay, so this is just the ideas. What is the string line? So the blue line showing here is the string line. So if you pick any point and you take the tangent, the tangent directions is the velocity directions of the flow. And this is the string line for if you put one particle with a different shape, and you take a look, the string line always parallel to the shape of the particle. But in that point, this is, we call that the stagnation point. And that means in here the velocity is equal to 0. Oh, I don't teach you detail in here because later we will have the detailed information for these formulas. Okay, so usually we define the fluid velocity. We need the reference point. So this is the reference point we pick here, and this is the particle A we would like to check. So for the particle A, we have the motion factors are A, and the motion factors if change with the time, so we can understand the fluid particle velocities. Okay, so it's just a very simple idea, so I don't stay here too much. So the second question, very important, how can we say the flow dimensions? So this is one example. This is the velocity field. And then we have the I, J, K unit vectors. And then each unit vector, that means each component, we have the velocity. And we use the U labels for the velocity along the x-axis. And we use the V as the velocity along the y-axis. And we use the W as the velocity along the z-axis. But each velocity is as a function of the x, y, z, t. Okay? So if I tell you this is the three-dimensional velocity field, that means the velocity include the I, J, K component. If I tell you this is 1D velocity field along the x directions, that means we don't have any component from J and K, because this is 1D and along the x direction. So we only have the I directions. And if I tell you this is 1D velocity field along x directions and the steady flow, that means the U is a function of x, y, z only. We don't have the t because this is a steady flow along the x directions. So the velocity didn't change with the time. So this is very simple definitions. If we tell you the 1 dimension or 2 dimension is a steady flow or unsteady flow, you need to understand what are the meanings. So these are the problems. I already tell you the velocity field can be given by these equations. And then, as I mentioned before, only I. So this is 1D or 2D. I don't tell you the answer because in Kahoot you can answer the answer. Okay. Later we will have a quiz highlight, and I will put these questions, and you can answer by yourself. And because we only have the I, and so this follow which directions. Don't confusing by x and y in here. This is x and y just control how large velocity it is. So also I plot the image in here. So you can take a look. As the x increase and the y increase, the arrow length increase also. That means this function can control the absolute velocity only. Don't control the directions. The direction only controlled by the unit vectors. Okay? So these are very important questions. Okay? So you need to answer the questions. Okay? And then if I change the velocity field like this, so we have the I, we have the J, and if you plot the velocity field, we'll like the arrow showing here. And if you connect all the arrow vectors, and you can define a different straight line, like this shape. Okay? Because the vectors, velocity vectors are tangent to the straight line. So the line, you just take the tangents. This is the velocity vectors at this point. Okay? So we need to do exercise. The exercise is quite simple. So we already have the velocity. And this is the 3-dimensional velocity field. And U defined by the 2x. And V defined it by the 2y. And the minus 4z is for the z component, W velocity. And I already tell you, you need to find out the 1 point, x, y, z, and the coordinate is 1, 1, 1. You need to find out the straight line, but need to pass through this point. So what is the straight line? But what the information you already have is we know the velocity field. As I mentioned, the straight line, the spatial, for the straight line only, the spatial gradient is always equal to what? It's always equal to the velocity gradient. Okay? So in that way, we can follow these ideas, try to find out the straight line functions. So first, we focus on the xy plane. And we know dx should be equal to the v divided u, right? Because the spatial gradient is equal to velocity gradient. And we already know the v is 2y. And the u is 2x. Okay, and we cancel out the 2, so it's y divided x. So the idea is we have the dy dx is actually equal to y divided x. And we do the same parameter we put together like this, and the x, and we do the integrations both sides. Okay, in that way we know the left hand side is long y, right? And the right hand side is long x, and we need to plus one constant values. We need to plus one constant values. And then we just do some movement. I'll just move the long x to left hand side, and you can see this here. As we know, the long minus another long x is equal to xy, and equal to c. So that means the exponential c power is equal to xy. But right now the c is unknown parameters. But we have the boundary condition is this straight line should be crossed over to this point. So we can put the x and y is equal to 1 and 1. Okay? And we put the 1 and 1 inside these equations. So that means the EC is equal to 1. So, 减 minus, okay.谢谢. Okay, so I just revise the formulas. Okay, so here again, here is y divided x, and then we put 1 and 1 inside, and then we know the c constants should be equal to 0, right? The same. Okay, so exactly we know this is, we define a function like this formula because the c is always, the constant value is always 0, so it's equal to 1. So along the xy planes, we know the function should be equal to x equal to y. Okay, this is the straight line functions on the xy plane. Okay, but if we change the different planes, because this is 3-dimensional problems, so we have another planes. Okay, so another plane now we are discuss with the xz plane. So again, you can calculate the dz, dx dz is equal to 2x and minus 4z, right? And we can recalculate this, and we just cancel out, and this is minus 2. Okay, so for these questions, it's equal to the dx divided the x, and I move the minus 2 here, and the right hand side is the dz divided z, and again we do the integrations. We do the integration both sides. Okay, so the left hand side is the minus 2 long x, and the right hand side is long z plus c. Okay, so you can just balance the equation. So we can take the minus 2 long x and the minus long z, and equal to c. Okay, and here you can multiply negative sign both sides. So you can rewrite the equation is equal to x 2 times 2 powers plus zone z and equal to c. Okay, so here you can rewrite. You exactly know the EC power is equal to x squared multiply z. Okay. Okay, so in that conditions, you know we have the xz point is also 1 and 1. So you put inside, finally you know the c is equal to 0 also. So finally you can just tell us the final stream function is like the formula showing here. This is a final stream function for the xz plane. Okay, so the idea quite simple. If the question is define the string line, and you only have the velocity field, so you need to follow the idea is spatial gradient equal to velocity gradient, and then you can determine the stream functions. This is the stream line functions for different plane along the xy and along the xz. Okay, so this is very basic ideas. If you know the stream line, and then you can understand the flow velocity properties. Okay, so I may start here. Okay, too complicated. Okay.